We are doing experiment number 5, buffer capacity today. So, well, just one thing I got to add there, the number, experiment number 5. Okay? So buffer capacity. Our objective for this particular experiment is we want to learn, first of all, how does buffer work? And then also we want to learn how to prepare a buffer solution. Now when we try to figure out how buffer works, and we will do a series of experiments there, and we prepare a buffer solution, we add sodium hydroxide to that buffer solution, and we also do a comparison by adding sodium hydroxide to water without the buffer. So we will try to compare the pH change in those two different situations. Okay? And then when we try to learn how to prepare a buffer solution, we need to use something that we call the Henderson-Hasselbalch equation. So pH of the buffer solution equals to pKa, Ka being the ionization constant for the weak acid, plus the log term of the molar concentration of conjugate base over the molar concentration of the acid. So this is the ratio here, the log term, and we have a concentration ratio here. So the terminology that we want to introduce here is that first of all, what is buffer? Well, we know from the lecture, buffer is a mixture of either a weak acid and its conjugate base, or a weak base with its conjugate acid. And so that is, when you have a mixture of that in aqueous solution, that solution actually resists the pH change. Hence the term buffer. We have a buffer solution that can resist the change of a pH there. Buffer capacity, well, this term refers to how much extra acid or base do we need to add into a fixed quantity of buffer solution in order to eventually change the pH. Say, buffer can resist pH change, but there's always a limit there. And if you have, say, 10 milliliter of buffer, and if you dump a gallon of acid in there, well, the pH will go down, right? And if you dump gallons of base in there, the pH will go up. But the thing here is that for that 10 milliliter of buffer solution, and when you first started adding acid or base to it, you don't see an obvious change in pH. And then by the time that you do see a pH going up or down by 1 or 2 units, and we say, well, you exceeded the buffer capacity. So that is also something that we will be looking into. And of course, as we do chemistry labs, and safety is always our top priority there, make sure you wear goggles and wear gloves when you handle chemicals. And for this particular experiment, you are supposed to come into the lab with a calculation already done, or the pre-lab calculation already done. So in the pre-lab here, we give you 2 scenarios. For buffer A, we want you to figure out how many grams we are using acetic acid, we're using sodium acetate. We want you to figure out how many grams of sodium acetate do we need to put into a 100 milliliter, 0.5 moles per liter acetic acid solution so that its buffer solution will have a pH of 4.0. So we need to do some calculation. And then the second scenario, we give you a different acidic solution there, and that is we have a 100 milliliter, 1.0 moles per liter acetic acid. How many grams of sodium acetate do you need to put in there so that the buffer solution will have a pH equals to 4? So, and this calculation, depending on where your lecture is, and this calculation can be a little bit confusing here. So I have a sample calculation on the whiteboard. So for buffer A, we need to figure out the mass of the sodium acetate, which is the conjugate base of the weak acid, acetic acid. So how many grams of sodium acetate do we need to add to 100 milliliter of 0.5 moles per liter acetic acid in order to have a pH equal to 4.0? Now we use something that we call Henderson-Hasselbalch equation. So we need the pH to be 4.0. Okay, so probably 2 decimals in there. And then Ka of the ionization constant for the weak acid, acetic acid, is 1.8 times 10 to the negative 5. So if you take the negative log of that number, you end up with 4.75. So we need the pH to be 4.0, and the pKa equals to 4.75, and plus the log term. Well, first we want to figure out the molar concentration of the conjugate base, sodium acetate. So in this case, we say, well, we don't know the concentration, so we assume it's X. And put it in the bracket, that represents the molar concentration. And the molar concentration of the acid that we gave you here, 0.5 moles per liter. So this would be the setup. And if you look at this equation, X is the only unknown. And doing a little bit algebraic maneuver, and then log and anti-log, you will be able to figure out the molar concentration of the sodium acetate solution should be somewhere around 0.08892 moles per liter. Okay? So this is the molarity that we need for the conjugate base. Well, based on the definition, molarity equals to moles over the volume, number of moles of solute over the volume. So in this case, the question is asking you how many grams of sodium acetate do we need? Well, we don't know. So mass in gram multiplied by the conversion factor, each mole of sodium acetate is 82.03 gram. And we got this information from the periodic table. You have sodium, you have carbons, hydrogens, and oxygens. You add everything together. Okay? So and if you look at this particular equation, the only unknown is the mass. And that is what the question is asking you for the pre-lab calculation. For buffer A, how many grams of sodium acetate do we need? Well, for 100 milliliter of the 0.5 moles per liter acetic acid, we need 0.7294 grams. So how do we prepare this buffer? We measure out this quantity of sodium acetate, and we take 100 milliliter of 0.5 moles per liter acetic acid, and we put that solid in there and have the mixture. And when we measure the pH of that solution should be somewhere around 4, based on the calculation here. Okay? So there's another part, and the second part for the pre-lab calculation, and here we have a different situation. We give you 100 milliliter, 1.0 moles per liter acetic acid. Again, Ka, acidic, the ionization constant for the acetic acid, 1.8 times 10 to the negative 5. Now we want the buffer solution to have a pH of 4.0. So how many grams of sodium acetate do we need? Well, the calculation for this one is identical to the setup of this side. So using this as an example, we solve for the mass. And in this case, we have 1.4587. And you may have noticed that this mass here, 1.45, is twice as much here. Because the concentration of the acid goes from 0.5 to 1.0 moles per liter. So the concentration of the acid doubles, and the concentration of the base, the conjugate base, also needs to double. And so in that case, we have the same ratio there. The ratio would stay the same. Okay? So these are the two pre-lab calculations that each of you should have done before you come in here, and I understand your lecture may be lagging a little bit behind, so we went through a detailed step-by-step calculation for buffer A. And I do encourage you to finish the calculation for buffer B before you actually do the experiment. And with that, we want to get into the demonstration part for how we perform the experiment and how do we determine the buffer capacity. So here in this experiment, we want to prepare two buffer solutions and we want to study the buffer capacity. So here in this beaker, I have the buffer A already prepared. I took 100 milliliter of the 0.5 moles per liter acetic acid, and I put it in a beaker. And then I put in 0.7294 gram of sodium acetate, and then mix it together. And you can see the pH is being measured here, and the pH of the solution equals to 4.05, a little bit over 4. Okay? So that has something to do with the accuracy of the measurement, or also the accuracy of the molar concentration of the stock solution there. But that's 4.05, 4.06, and that's within the allowable errors in the experiment there. So this is the buffer solution that we prepared. So how do you do buffer B? Well, the same thing here. You get 1.45 grams of sodium acetate, and you will take 100 milliliter of the 1 moles per liter acetic acid solution, and then you put that 1.45 gram of the sodium acetate into that 100 milliliter solution. If you test the pH there, you should end up with a pH somewhere around 4.0. 4.05, somewhere in that neighborhood. Okay, so the lab procedure here, and if you look at the lab menu there, lab procedure calls for taking 10 milliliter of this buffer solution, putting it in a beaker, and then you add 15 milliliters water. Now keep in mind, in the lecture there, we're talking about the buffer capacity. The pH of the buffer does not depend on the concentration of each individual chemical in it. Rather, it depends on the ratio of the concentration between the two chemicals. In this case, the sodium acetate and acetic acid. Okay? So if you add water, if you dilute the solution, both concentrations got diluted. And therefore, it doesn't change the pH. And so this particular solution, we put 10 milliliter of the buffer A in here. We added 15 milliliters of water in it. And if you test the pH of this solution, and you can see the pH is still somewhere around 4.05. Okay, so the pH of the buffer solution does not change when you dilute, add more water to it, or when you remove the water from it. Because when you change the quantity of water, you're changing the concentration for both the acid, weak acid, and the conjugate base, and the pH remains the same. So how do we test the buffer capacity? In your lab manual, we ask you to use the lab quest to measure the pH as we add sodium hydroxide from the burette into the buffer solution. Now, it even asks you to record the information so that you end up with a nice titration curve. So what we are doing here in this demonstration, we're just going to see how much sodium hydroxide does it take in order for the pH to jump up by 2 units. Okay? You know, every unit in pH jump represents a 10-fold increase in concentration for the hydroxide ion. Okay? So 2 units jump, and that's a huge jump in terms of the concentration. So right now we're going to put the pH probe into our buffer solution. Okay, we're going to put the pH probe into our buffer solution, and then we will start adding sodium hydroxide from the burette into the buffer solution. And we will see how much does it take in order for the pH of the buffer solution to jump up to 6. Okay? So we will add, your lab manual asks you to add the sodium hydroxide in 1 milliliter increment. So here we have 0 milliliter reading, the initial reading for the burette. We will just put one milliliter in there. Okay? And then when you stir it, you see the pH start to change a little bit, but not by much. And it was 4.05, and now it's 4.35. So the pH did go up a little bit, and this is probably, it shouldn't really go up this much, and it could be because I haven't done a thorough mixing yet. So by mixing the solution with the glass rod, and you can see the pH stabilize a little bit. So we added 1 milliliter of sodium hydroxide, and pH didn't jump much, and we can put another milliliter in there. Okay, so we put another milliliter of sodium hydroxide in, and we stir the mixture there. Okay, and the pH still stays in the 4.5 range. So now by adding 2 milliliters of sodium hydroxide, we see the pH actually went up by half a unit. So, and keep adding sodium hydroxide until we have a 2-unit jump. We do another milliliter here. We have somewhere around 4.6, 4.7. So the pH jumps up to by a 0.7 unit there. And we can do another milliliter. Okay. So we're almost at 5 now, 4.87. So we'll just keep going. So we've been adding 5 milliliters of sodium hydroxide now. The pH is at 4.99. So almost a 1 unit jump. Okay? So we can keep going with another milliliter. Two mils in. So I've added a total of 10.5, close to 10.5, 10.6 milliliter of sodium hydroxide. And then if you look at the pH now, it says 6.00. So we had 4.05 at the beginning for the buffer solution. In order for the pH to increase by 2 units, we have to add more than 10 milliliters of sodium hydroxide. So when we ask you the question there, what is the buffer capacity? Well, you can say for 10 milliliter of this particular buffer solution, it takes 10.5 milliliters of sodium hydroxide, and the concentration of sodium hydroxide is 0.5 moles per liter. So it takes 10.5 milliliter of 0.5 moles per liter sodium hydroxide to have a 2-unit jump. Okay? And we also want you to compare between buffer A and buffer B, as well as between buffer and pure water. So we will do a quick demonstration for the buffer capacity for the pH change of water. So we will get 25 milliliters of water. Okay, so we can use another beaker, and we will get some water from the deionized water. So this is roughly about 25 milliliters of the deionized water. And we can test the pH of this water. Okay? And you put the pH probe into the deionized water. Should be somewhere around 7, but it didn't say 7. On the pH meter there, and it actually says 4 point something. Okay? Well, this is pure water, deionized water we added in there. Does it have the same capacity to resist the pH change? Well, let's see. We will just put 1 milliliter of sodium hydroxide in it. Okay. The starting pH, remember, is somewhere around 4. Okay? And now we added 1 milliliter of sodium hydroxide in it. Thoroughly mixing it, the pH is let it stabilize a little bit. So we start the pH around 4, which is not an accurate number to begin with. For deionized water, it should be somewhere around 7. Okay? But in any case, when we added 1 milliliter of the sodium hydroxide into the solution, into that 25 milliliter water, you see the pH went from 4 all the way up to 11. So in this case, the pure water does not have any capability to resist the pH change. Once you put a small quantity of acid or base in, you are going to see a drastic change in pH. Okay? So that's how the buffer and the pure water works. And you ask, why is this important? Well, buffer solution is pretty much everywhere in biological system, because your cells and your tissues, they will not be able to survive with sudden buffer change there. So most of the biological fluids, and those are the buffer solutions, when you dump in large quantity of acid or base, and the pH of the solution will stay quite stabilized, will stay quite stable without a sudden change of pH. And that's how we can survive with the sudden change. Like if you dump some Coca-Cola into your stomach, and that thing, the stomach fluid actually has a pH somewhere very low, somewhere the pH of 1.0, 2.0. And the Coke has a pH of 2.39. And if you put the soda into your body there, well, you don't want that pH inside your cell. You don't want the pH to change suddenly. Well, you have a lot of buffer solution in your body, therefore you don't see a sudden change in pH. That's how the cells can actually survive the addition of acid or base, whatever you put into your body there. Okay, so another part of the activity, we ask you to prepare another buffer solution, buffer B, and then you're going to compare how much sodium hydroxide does buffer B takes in order for the pH to jump 2 units. And I will let you go back to the experiment and do these experiments. And so once you finish the experiment there, you can start writing up your lab report, and then summarize your result and start writing up your lab report.